This cosmic cloud is a ticking time bomb of secrets. The Crab Nebula is the scattered remains of a star whose violent death was seen from Earth in the year 1054. We are about to journey deep into its heart to uncover 30 of its most bizarre and mind-bending phenomena. You will discover a universe where stars spin 30 times every second, and reality itself seems to bend. How can a celestial object suddenly flare with the energy of 100,000 suns? What mysterious force creates illusions of motion faster than light? By the end of this exploration, you will see this beautiful nebula not as a static picture, but as a dynamic cosmic laboratory that challenges everything we think we know. What single force in the universe do you find most mysterious? At the very heart of this cosmic wreckage lies a monster of pure energy. The Crab Pulsar is a city-sized ball of ultra-dense matter, spinning at an almost inconceivable rate. 30 times every second, this neutron star completes a full rotation, whipping around faster than a helicopter blade. This frantic spin powers a dynamo of unimaginable force, generating a magnetic field so powerful it could strip the data from every credit card on Earth from a distance of 1,000 light-years. It acts as a cosmic lighthouse, sweeping twin beams of radiation across the galaxy with a rhythm so precise it rivals atomic clocks. Yet, this seemingly perfect celestial metronome has a strange and unpredictable habit. Astronomers have observed sudden, violent events they call glitches. Without any warning, the pulsar's spin will suddenly speed up. It is as if a giant, unseen hand has given it a sharp, unexpected push. These glitches are more than just a curiosity. They are a profound challenge to our understanding of physics. What could possibly cause an object with the mass of a sun compressed into such a small space to suddenly change its rotation? The leading theories point to the bizarre nature of its interior. Some scientists believe the immense pressure creates a superfluid, a strange state of matter that flows without any friction. A sudden shift of this internal superfluid could transfer energy to the star's solid crust, causing it to spin faster in a cosmic stumble. Others propose these are starquakes, where the neutron star's incredibly dense crust fractures and rearranges itself, changing its shape and thus its spin. Each glitch is a message from a realm where matter exists in states we cannot create on Earth. A brief glimpse into the secret life of a dead star. This cosmic metronome is not the only source of strange behavior. The entire nebula itself can suddenly erupt with a ferocity that defies all expectation. For decades, scientists viewed the Crab Nebula as a steady, predictable source of energy, a cosmic constant against which other objects could be measured. That comforting notion was completely shattered by data from the Fermi and Agile space telescopes. They witnessed the impossible, giant gamma-ray flares that erupt from the nebula without warning. In a matter of mere hours, the entire structure can double its brightness in the highest energy form of light. These are not gentle flickers, but violent outbursts that release photons with energies far beyond what any known process in the nebula should be able to produce. Imagine a quiet lake suddenly launching a geyser of molten metal into the sky. This phenomenon has become a top priority mystery in high-energy astrophysics, forcing a complete rethinking of how these cosmic engines operate. How can a cloud of gas and dust, the remnant of an ancient explosion, suddenly generate such concentrated power? The leading suspect is a process known as magnetic reconnection. Picture the nebula's tangled magnetic fields as a vast collection of overstretched rubber bands. If these bands snap and reconnect into a new, simpler configuration, they release a colossal amount of stored energy all at once, like a cosmic short circuit. This event could violently fling particles to velocities approaching the speed of light, and when these particles are whipped around by magnetic fields, they radiate the immense gamma-ray flares we observe. Yet the exact trigger for this violent release remains hidden, a fundamental puzzle at the very edge of our comprehension. These gamma-ray flares are not the only visual trick the Crab Nebula has to play. Near the central pulsar, the Hubble Space Telescope has captured something that seems to break the universe's ultimate speed limit. They are called wisps, and they are dynamic, wave-like structures that appear to race outward at speeds faster than light. This is not some blurry photographic artifact, but a clear and repeated observation of what looks like pure impossibility. How can anything travel faster than the cosmic speed limit set by light itself? The secret lies not in the laws of physics breaking, but in a breathtaking cosmic illusion. The wisps themselves are not solid objects, but are thought to be shock waves, the visible fronts of a titanic collision. The pulsar constantly blows out a hurricane of particles, a relativistic wind moving at nearly the speed of light. When this supersonic wind slams into the slower-moving gas and dust of the surrounding nebula, it creates a visible boundary of intense energy. Because this shock front is moving almost directly towards us, its own light has a much shorter distance to travel to reach our telescopes with each passing moment. It is like a surfacer riding a wave directly towards the beach. From your perspective on the shore, the surfer appears to be moving across the water much faster than the wave itself is actually traveling. This relativistic projection effect makes the wisps appear to move at 6 or 7 times the speed of light. While no material object is truly breaking that barrier, the illusion provides a stunning and direct visualization of the raw power being unleashed from the pulsar. A continuous, invisible hurricane of particles crashing into the ancient stellar debris with enough force to create phantoms of motion that defy our everyday senses. This illusion of impossible speed is just one layer of the Crab Nebula's hidden reality. Beyond the shimmering gas clouds captured by the Hubble telescope lies something completely invisible to our eyes, a vast and energetic halo. Modern gamma-ray telescopes have pierced the veil, revealing that the nebula we see is merely the bright, dense core of a much larger and more powerful structure. This halo is a sprawling cloud of the highest energy particles, stretching far into the space surrounding the familiar crab-like shape. Its discovery fundamentally changed our understanding of the nebula's true scale and power. The ghostly halo tells us that the particle acceleration happening here is far more extensive and energetic than anyone had ever dreamed. It acts as a natural particle accelerator on a cosmic scale, one that dwarfs anything we could ever hope to build on Earth. Think of the visible nebula as the bright, hot engine of a car, and this newly discovered halo as the immense, invisible cloud of exhaust and energy billowing out from it, filling a volume of space that is almost too large to comprehend. How do these particles reach such incredible energies? They are caught in the pulsar's relentless magnetic storm, whipped back and forth across vast distances until they are moving at nearly the speed of light. This process is so efficient that it creates a persistent, high-energy glow that we can only detect with our most advanced instruments. The existence of this halo means the Crab Nebula's influence on its cosmic neighborhood is far greater than its beautiful, visible form suggests. A reminder that the most powerful forces in the universe are often the ones we cannot see. These high-energy particles racing through the halo have a distinct and dynamic signature closer to the pulsar itself. The Chandra X-ray Observatory has revealed an intricate, glowing ring that encircles the central star. This is not a static structure of gas, but a shimmering loop of pure energy, a crown of intense X-rays that pulses with activity. The ring is created by the most energetic electrons in the nebula, forced to spiral at nearly the speed of light along the pulsar's powerful magnetic field lines. As these electrons are whipped around, they shed their immense energy not as visible light, but as the penetrating X-rays that Chandra can see. What makes this inner ring so fascinating is that it is never the same from one observation to the next. It is a living, breathing entity in a cosmic sense. Bright knots form and fade within the ring, and the entire structure shifts and writhes over time, like a glowing lasso being shaken by an invisible hand. This constant motion provides astronomers with a rare and precious opportunity. We are watching a cosmic laboratory in real time, a place where we can directly witness the mechanisms of particle acceleration. The turbulent environment just outside the pulsar is a chaotic maelstrom, and these moving knots are thought to be sites where magnetic fields are reconfigured, giving particles an extra violent kick. By tracking how these features brighten, dim, and move, scientists can test their theories about how a dead star's fury is converted into a storm of radiation, one that shapes the entire nebula around it. The shimmering X-ray ring is a testament to the raw power being unleashed at the nebula's core. But this energy reveals itself in other, more persistent ways. For decades, astronomers have been tracking a different kind of signal from the crab, one that presents a profound and lasting mystery. In the realm of radio waves, this cosmic cloud has refused to fade. Most supernova remnants grow steadily dimmer in radio light as they expand into the void, their energy dissipating over centuries. The Crab Nebula, however, has defied this expectation. Its radio brightness has remained stubbornly, remarkably stable for as long as we have been able to measure it. This is not a fleeting flare or a temporary spike, but a constant, unwavering hum that has persisted through generations of human observation. How can this be? A cloud of gas and dust, flung outward by a cataclysm 1,000 years ago, should be cooling down and spreading out, its radio voice growing fainter with each passing year. The fact that it has not faded implies something extraordinary is happening inside. There must be a continuous, highly efficient engine at work, one that constantly injects fresh energy and replenishes the population of high-speed electrons that generate the radio waves we detect. This is like a campfire that never burns out, not because you keep adding large logs, but because an invisible hand is tirelessly feeding it a perfect supply of new kindling, maintaining a perfect, steady flame. The pulsar is the obvious candidate for this energy source, but the exact process of how it so efficiently fuels the entire nebula, keeping its radio glow so consistent across such vast scales, remains one of the most enduring puzzles in astrophysics. What secret mechanism is at work, tirelessly repowering this ancient stellar corpse to sing the same unwavering note into the darkness? That same relentless engine also projects its power along narrow, focused beams. From the very poles of the spinning pulsar, two powerful jets of particles and magnetic fields blast outward, carving their way through the surrounding chaos. One of these jets, aimed almost directly at Earth, reveals an even more intricate spectacle. Along its length, brilliant knots of material appear to form and race away at speeds close to that of light. These are not mere clumps of gas, but intense concentrations of energy, shining with a fierce blue-white light in our telescopes. Watching them is like watching bullets fired from a cosmic rifle, each one a separate packet of fury launched from the heart of the dead star. Their formation is a direct result of the violent struggle at the nebula's core. The pulsar's wind is not a smooth, steady flow, but a turbulent, gusting river. As this torrent rams into the slower-moving material of the nebula, it can create instabilities, much like a fast-moving stream of water will break into distinct droplets if you run your finger through it. These knots are thought to be born from such interactions, where the magnetic fields and particle flows become so tangled that they pinch off into these brilliant, self-contained blobs. Their rapid motion offers astronomers a unique probe into the engine's workings. By tracking how quickly these knots accelerate and how they change as they travel, scientists can measure the incredible forces at play just outside the pulsar. Each knot is a message in a bottle, carrying encrypted information about the power, the pressure, and the magnetic fury that launched it on its one-way journey across the nebula. While one jet blazes a brilliant trail across the nebula, its counterpart on the opposite side tells a more subtle story. This second stream of energy, known as the counterjet, is often far dimmer and more difficult to observe, creating a profound asymmetry in the heart of the crab. Why would a spinning star, which should be symmetrical, fire off such lopsided beams? This imbalance is a crucial clue, a cosmic fingerprint left over from the star's violent birth. One possible explanation lies in a relativistic effect called Doppler boosting. The jet pointed nearly towards us is made brighter because its light is compressed and amplified as it races in our direction. Much like the sound of an approaching siren seems to sharpen and intensify. The counterjet, fleeing from us, has its light stretched and dimmed. But this light trick may not be the whole story. The surrounding environment is not a perfect vacuum. It is a chaotic wreckage of ancient stellar material. The counterjet might be plowing into a denser, more resistant wall of gas and dust, causing it to dissipate its energy and appear fainter. Or the pulsar's own spin axis could be tilted in such a way that one jet finds a clearer path out of the nebula's core while the other struggles. Each of these possibilities points back to the moment of the supernova itself. The final dying kick of the exploding star may have sent the newborn neutron star spinning with a distinct wobble, or it could have ejected its debris in an uneven shell. By studying this lopsided structure, we are essentially reading the forensic report of a stellar catastrophe, uncovering the hidden forces that shaped this cosmic engine from its very first second of life. This brilliant, shimmering light we see is not a simple fire. The entire visible glow of the Crab Nebula is a specific and violent kind of light known as synchrotron radiation. To understand this, picture an electron as a tiny, hyperactive marble. Now, send that marble hurtling through a maze of powerful magnetic fields at almost the speed of light. The electron cannot travel in a straight line. The magnetic forces constantly wrench its path, forcing it into a tight, spiraling corkscrew. This violent, forced change of direction causes the electron to shed energy, and it radiates that energy away as light. This is synchrotron radiation, a process so efficient it lights up the entire nebula with a fierce, polarized glow. It is the same basic principle used in human-made particle accelerators, but here it operates on a cosmic scale, with nature's magnets and natural particle guns. The entire nebula acts as a colossal synchrotron machine, its tangled magnetic fields and frantic electrons combining to produce the beautiful, ethereal light that fills our telescope images. Yet for all its brilliance, this light hides a fundamental mystery that physicists call the injection problem. We can see the electrons spiraling and glowing, but we do not know exactly where they get their initial, monstrous kick of speed. How are these particles, which start as relatively slow-moving stellar debris, accelerated to over 99% of the speed of light? The pulsar's wind is the ultimate source of energy, but the precise location and mechanism of this transfer is the true enigma. Is it at the shock wave where the pulsar wind slams into the nebula? Is it deep within the turbulent inner ring, where magnetic fields snap and reconnect? Or is it a combination of many processes happening throughout the cloud? Identifying this cosmic starting line, the exact point where ordinary particles are transformed into ultra-relativistic bullets, remains one of the most active and crucial quests in understanding the Crab Nebula. It is the search for the engine's ignition switch, the moment the fire is truly lit. Even the brilliant synchrotron glow cannot account for all the Crab Nebula's secrets. Nestled within its light is a mysterious infrared warmth, a puzzling excess of energy that should not be there. The Spitzer Space Telescope clearly detected this strange emission, a heat signature that our standard models of the nebula simply cannot explain. If the visible light is the fierce blue-white fire of electrons spiraling in magnetic fields, this infrared glow is something else entirely, a deep, ruddy heat that whispers of a different physical process at work. So what is producing this unexplained warmth? One compelling theory points to dust. The nebula could be filled with tiny, solid grains, the soot and sand of the shattered star. These microscopic particles would be heated by the intense radiation from the pulsar and the synchrotron glow, until they themselves begin to radiate their own thermal energy, glowing with a persistent infrared light. Yet this simple explanation is fraught with its own problems. The environment inside the Crab Nebula is brutally violent, flooded with high-energy radiation that should shred and destroy such delicate dust grains almost as soon as they form. How could any dust possibly survive there long enough to produce such a strong and steady signal? This leads to another fascinating possibility. The emission might not be from dust at all, but from large, complex molecules known as polycyclic aromatic hydrocarbons. These carbon-based molecules can emit strongly in the infrared, and their presence would suggest that the nebula is not just a cloud of simple gas and elementary particles, but a more complex chemical factory than anyone expected. This unidentified infrared glow forces us to ask what the Crab Nebula is truly made of. Is its composition far richer and more varied than we ever imagined, hiding a reservoir of solid material and complex compounds within its storm of radiation? This thermal mystery adds a profound new layer to the nebula, transforming it from a purely energetic object into a potential cosmic chemist. This infrared warmth and chemical complexity force us to look back in time, to the very star whose death created this cosmic laboratory. The ghost of that progenitor star haunts the nebula, and its identity is a puzzle in itself. Based on the amount of material we see and the nature of the pulsar it left behind, the star that exploded in 1054 was likely not a colossal giant. It was probably a star of between 8 and 10 times the mass of our own Sun. This places it in a very special and precarious category. Such a star is not heavy enough to die in the most common type of supernova, which involves the collapse of an iron core. Instead, it is the prime candidate for a far rarer and more peculiar event, an electron capture supernova. In its final days, the star's core would have been composed of oxygen, neon, and magnesium. Under the immense pressure of the star's own weight, a bizarre quantum process would have begun. Electrons, the tiny particles orbiting the atomic nucleus, would have been forcibly crushed into the protons of the neon and magnesium atoms, transforming them into neutrons. This process, electron capture, is a cosmic robbery. It steals the very pressure that was supporting the core against its own gravity. In an instant, that support vanishes. The core catastrophically implodes, triggering a shockwave that blasts the star's outer layers into space. This is not the violent death of a heavyweight champion, but the sudden, unstable collapse of a star that was balanced on a knife's edge. It is a specific kind of stellar suicide that leaves behind a specific kind of remnant, a neutron star with a mass right at the theoretical lower limit for such objects. The Crab Pulsar is that remnant, a zombie star born from this rare and delicate process, whose frantic spinning continues to animate the entire nebula we see today. This intricate web of glowing filaments is far more than a beautiful cosmic sculpture. It is a high-speed forensic map of the original explosion. For nearly 1,000 years, this network of ionized gas has been racing outward, and modern telescopes have captured its motion in stunning time lapses. Watch these images over years, and you can see the entire structure growing, its delicate threads of hydrogen and helium expanding at speeds exceeding 1,000 kilometers per second. That is fast enough to travel from Earth to the Moon in under 7 minutes. Each filament is a piece of the original star's outer layers, now heated to incandescence and branded with a unique chemical signature. By meticulously tracking the velocity and direction of each thread, astronomers can perform a kind of cosmic reconstruction. It is like studying the pattern of shrapnel from a bomb blast to determine where the bomb was placed and how powerful it was. The fastest-moving filaments were likely ejected from the deepest layers of the star, catapulted by the initial shockwave. Slower, more tangled regions might represent material that encountered resistance or was caught in turbulent eddies within the expanding cloud. This ever-shifting labyrinth provides a dynamic, three-dimensional view of the supernova's fury, a fossilized echo of the blast wave that is still actively carving its way through interstellar space. What secrets about that single, cataclysmic day in 1054 are still encoded in the frantic, beautiful dance of these ancient stellar veins? These racing filaments are more than just speed demons. They are cosmic chemists holding the star's final recipe. When astronomers analyze their light, they discover a composition that is distinctly odd. There is an overabundance of helium, far more than standard models predict for a star of this type. Mixed in with it is a strange brew of other elements like carbon, oxygen, and nitrogen, but in proportions that do not neatly align with what we know about stellar life cycles. This peculiar chemistry is a direct fingerprint, a forensic report of the nuclear fusion processes that were raging inside the massive star in the moments just before its death. Think of a star's interior as a layered onion. Deep in the core, fusion creates heavier elements, while the outer layers remain mostly hydrogen and helium. For the Crab Nebula's filaments to show this specific mix, those layers must have been violently stirred together before the final explosion. This points to a period of intense, chaotic mixing in the star's final days, a turbulent prelude to the supernova. Convection currents may have dragged material from deep within the star up to its surface, while simultaneously pulling hydrogen from the surface down into hotter regions where it could fuse. The result is a scrambled stellar interior, a chemical anomaly that our clean, theoretical models did not fully anticipate. Why would a star behave so erratically in its final hours? This strange mix forces us to reconsider the final, unstable dance of nuclear reactions that precedes a supernova, suggesting that the death of a star is a far more complex and messy affair than we once believed. This polarized light holds the map to the nebula's invisible skeleton. The beautiful glow we see is not random. Its light waves are highly organized, vibrating with a strong preference for a single direction. This is the definitive signature of synchrotron radiation, the same process that lights up the nebula, but it tells us something more profound. It reveals that the magnetic fields controlling the electrons are not a chaotic jumble, but possess a hidden, large-scale order. Imagine looking at a vast, shimmering lake on a windy day. If the light reflecting off the water was polarized, it would tell you the precise direction the wind was blowing across the entire surface. The polarization of the Crab Nebula's light works in the same way, acting as a cosmic compass that traces the direction of its powerful magnetic fields. When astronomers create detailed maps from this polarized light, a complex and beautiful architecture emerges. The magnetic fields are not simple straight lines radiating from the pulsar. They are woven into an intricate, tangled web that drapes throughout the entire structure. This magnetic tapestry is the nebula's true framework, an invisible scaffold that dictates the movement of every high-speed electron. The particles are not free to go wherever they please. They are forced to spiral along these magnetic highways, and their brilliant synchrotron light shines brightest where the field lines are most tightly bundled and orderly. This is why the nebula has its filamentary, stringy appearance. The visible glow is literally painting the lines of force of this immense, cosmic magnet. The polarization maps show us that the magnetic field is strongest near the pulsar and in the bright inner ring, where the frenzy of particle acceleration is most intense, and then becomes more disorganized in the outer filaments. This hidden structure does more than just shape the light. It confines and guides the relativistic wind from the pulsar, preventing it from dissipating too quickly and ultimately governing the nebula's long-term evolution. The very form of this cosmic cloud, the reason it looks the way it does, is written in the silent, polarized language of its light. This invisible magnetic skeleton channels particles to energies that defy human engineering. The Crab Nebula is a source of the highest energy photons ever detected, gamma rays in the tera-electronvolt range. To understand this scale, A tera-electronvolt is a unit of energy 1,000,000,000,000 times more powerful than the energy of visible light. These are not just high-energy photons. They are the cosmic equivalent of armor-piercing rounds, carrying forces that push the very limits of what we believe is possible. Ground-based telescopes like Veritas and HESS do not look like traditional observatories. They use vast arrays of mirrors to detect the faint, blue flashes of light that these gamma rays create when they strike the Earth's atmosphere. The fact that they can consistently detect these rays from the Crab Nebula means something truly extraordinary is happening inside that cloud. The particles producing this light must be accelerated to energies far beyond the capabilities of our greatest machine, the Large Hadron Collider. Our most powerful particle accelerator on Earth can only reach energies a fraction of what the Crab Nebula achieves naturally. This makes the Crab a unique and essential cosmic benchmark, a natural laboratory against which we must test all our theories of particle acceleration. How does this chaotic cloud of gas accomplish what requires kilometers of precisely tuned machinery on Earth? The process is a cosmic slingshot of unimaginable power. Electrons are caught in the turbulent magnetic storms near the pulsar, whipped back and forth across vast distances. Each pass gives them another violent kick, boosting their speed until they are traveling so close to light speed that their mass effectively becomes immense. When these ultra-relativistic particles then collide with lower-energy photons or spiral in magnetic fields, they can transfer that staggering energy, creating the tera-electronvolt gamma rays we detect. The Crab Nebula is not just a beautiful remnant. It is a natural super collider, operating on a scale and with an efficiency that we are only beginning to comprehend. This brilliant nebula even casts a shadow upon the oldest light in the universe. To see it, we must look beyond the Crab itself, to the faint, cold glow of the cosmic microwave background. This is the remnant heat from the Big Bang, a uniform sea of low-energy photons that fills every corner of space. When the Crab Nebula's own high-speed electrons encounter these ancient photons, a remarkable transformation occurs. The electrons, moving at nearly the speed of light, can collide with these background photons and impart a tremendous amount of energy to them, effectively kicking them up in frequency. This process, known as inverse Compton scattering, creates a subtle but measurable dimple in the cosmic microwave background, precisely where the Crab Nebula sits in the sky. It is as if the nebula's own energetic particles are blotting out the primordial light behind it, casting a faint, high-energy shadow. This is not a shadow of darkness, but one of altered energy, a specific distortion that only our most sensitive instruments can detect. Why would astronomers go to such lengths to find this ghostly imprint? Because this shadow holds unique information about the nebula's secret population of particles. By analyzing the precise shape and depth of this distortion, scientists can deduce the density and energy of the relativistic electrons that caused it, offering an independent way to measure the nebula's power. It also probes the strength of the magnetic fields that confine those electrons. This cosmic shadow is a perfect example of how astronomers use one phenomenon to illuminate another, turning the entire universe into a vast, interconnected laboratory where even the echo of creation can be used to understand the fury of a dead star. The very heart of the Crab Nebula is on the run. This cosmic engine, the spinning pulsar, is not sitting placidly at the center of the wreckage it created. Instead, it is racing through space at an astonishing speed of 375,000 miles per hour. At that velocity, you could travel from Earth to the Moon in well under an hour. This incredible motion, known as its proper motion, was not a gentle drift but a violent, single shove delivered in the instant of its birth. When the progenitor's star went supernova, the explosion was not a perfectly symmetrical blast. Imagine a grenade that does not explode evenly in all directions, but has one side that is just slightly more powerful than the other. That imbalance, that cosmic lopsidedness, would have given the newborn neutron star a powerful kick, like a rocket engine firing from one side of the collapsing core. This is the most likely explanation for the pulsar's breakneck speed. It is a bullet fired from a cosmic gun, still carrying the momentum from that single, asymmetrical detonation over 1,000 years ago. This has a profound consequence for the future of this iconic nebula. The pulsar is moving so fast that it is slowly but surely leaving its own glowing remnant behind. The very object that energizes the entire cloud, that powers its shimmering synchrotron glow and drives its violent flares, is destined for an escape. In tens of thousands of years, the pulsar will have traveled completely outside the expanding shell of gas. It will drift alone through the interstellar void, a dark, spinning cinder, while the beautiful nebula it left behind slowly fades, its central engine gone, its brilliant light finally beginning to dim. The Crab Nebula, as we know it, is a temporary masterpiece, a partnership between a runaway star and its fading echo. This dual nature is the key to the Crab Nebula's enduring brilliance. Most supernova remnants are like a single, spectacular firework. They explode with a blinding flash, and then we watch the glowing, expanding shell of debris slowly fade as it cools. Their light comes from the heat of the original blast and from the shock wave as it plows into interstellar gas. The crab is fundamentally different. It is a firework that never went out, because someone left a blowtorch burning at its center. The beautiful, intricate structure we see is not just the fading remnant of an ancient explosion. It is a pulsar wind nebula. This means its primary source of light is not the one-time energy of the blast, but the continuous, furious output of the spinning pulsar. The pulsar's relentless wind of particles and its powerful magnetic field inflate a bubble of high-energy radiation within the expanding shell of stellar debris. It is this ongoing energy injection that constantly re-energizes the electrons, making them shine with that fierce synchrotron glow, and preventing the nebula from fading as quickly as its cousins. So the crab is two things at once: the expanding fossil of a stellar catastrophe and a living, breathing engine powered by its undead heart. This duality solves the mystery of its unwavering radio brightness and explains why it remains so violently active nearly 1,000 years after the star died. How many other cosmic wonders hide such a double life, where the ghost of the star never truly rests? This cosmic engine, racing through space, has a birthday we know with astonishing precision. While we study its high-energy fury with our most advanced technology, its story was first written in the skies over 1,000 years ago. In the year 1054, a new star blazed to life in the constellation of Taurus. It was not a faint twinkle, but a celestial beacon so brilliant it was visible in broad daylight for 23 days, and it remained a haunting presence in the night sky for nearly 2 years before finally fading from view. This was not an event missed by the world. Meticulous court astronomers in China documented this guest star with careful detail, noting its position and its unprecedented brightness. Scholars in the Islamic world also recorded its sudden appearance, and there is compelling evidence that Native American peoples, like the ancestral Pueblones of the American Southwest, may have captured its image in a petroglyph, a star-shaped carving next to a crescent moon that matches the astronomical arrangement from that exact time. This global observation is a gift to modern science. That historical record is the unshakable foundation upon which our entire understanding of the Crab Nebula is built. It gives us the exact age of this object. We know, without any doubt, that the light we see today is the aftermath of a stellar explosion that humanity witnessed in 1054. This turns the nebula from a mere subject of study into a living timeline. It allows us to measure exactly how fast the filaments have been expanding for 1,000 years. We can calculate the exact energy of the original blast and trace how the pulsar has spun down over centuries. This single, well-documented event is the cornerstone of supernova science, the first and most crucial data point that connects a violent stellar death in the deep cosmos to the human experience of wonder recorded on Earth. The brilliant death of the Crab's star might not have been a solitary event. A compelling line of inquiry suggests its progenitor was not alone, but locked in a gravitational dance with a companion star. When the supernova erupted, this binary partner would have faced a cosmic cataclysm. The sudden, violent loss of over half the system's mass in the explosion would have sent the surviving star flying, like a stone released from a sling. It could have been flung out on a high-speed escape trajectory, becoming a runaway star racing across the galaxy. Alternatively, the blast might have been so overwhelming that the companion was not ejected, but utterly consumed, shredded and swallowed by the expanding fireball. This missing companion transforms the nebula's story into a grand cosmic detective case. Astronomers are actively scouring the space around the Crab, searching for any star moving with the precise, high velocity that would mark it as the original partner. They look for a sun that seems out of place, racing along a path that, if traced backwards 1,000 years, leads directly to the heart of the explosion. Finding this stellar fugitive would be a monumental discovery. Its very existence, or its confirmed absence, would provide crucial evidence for the type of supernova that occurred. A successful ejection would strongly support the electron capture model, as the mechanics of that specific implosion are particularly effective at flinging a companion away. This search for a ghost star is more than just filling in a blank in the story. It is an attempt to understand the very conditions of the stellar marriage that ended in such a spectacular, public divorce. Even the nebula's ultraviolet glow refuses to stay still. The Crab Nebula shines brightly in the ultraviolet part of the spectrum, a fierce, high-energy light that lies just beyond the blue end of what our eyes can see. But this is not a steady beacon. Observations from ultraviolet telescopes reveal a nebula that flickers and changes its brightness, a subtle but definite variability that points to a constant state of flux deep within its core. This ultraviolet light is generated by the same population of fast-moving electrons that create the visible synchrotron radiation. But these are even more energetic particles. Their unpredictable flickering means the engine at the heart of the Crab is not running smoothly. It is sputtering and surging in real time. The changes are directly linked to the chaotic environment near the pulsar and within the glowing inner ring. Imagine a powerful fire hose feeding a vast, shimmering fountain. If someone were to rapidly adjust the water pressure at the nozzle, the entire structure of the spray would shimmer and shift in response. The variable ultraviolet output is that shimmer. It is a direct echo of changes in the rate at which new, high-energy particles are being injected into the system, or of sudden reconfigurations of the magnetic fields that force those particles to radiate their energy away. A small magnetic reconnection event, a minor starquake on the pulsar, or a temporary surge in its relentless wind can all send a ripple through the nebula's energy balance, one that manifests as a detectable flicker in the ultraviolet light we observe from Earth. This constant, subtle dance of light proves that the Crab is not a settled relic, but a living system whose heart beats with an irregular, energetic rhythm. Those sudden, violent gamma-ray flares demand a cosmic culprit capable of unleashing such concentrated fury. The prime suspect in this high-energy mystery is a process called magnetic reconnection. Picture the nebula not as a calm cloud, but as a seething ocean of magnetic force. The pulsar's relentless wind and its frantic spin twist these magnetic field lines into knots of unimaginable tension. They become like a vast collection of overstretched rubber bands, storing colossal energy as they are wound tighter and tighter. Magnetic reconnection is the moment these bands suddenly snap, breaking their original configuration and violently reconnecting into a new, simpler arrangement. In that instant of snapping, all the pent-up energy is released in a catastrophic burst. It is a cosmic short circuit on a staggering scale. This sudden release does not just create a flash of light, it acts as a natural particle accelerator of breathtaking efficiency. The explosive reconnection flings electrons and other particles to velocities so close to the speed of light that their energy becomes almost incomprehensible. When these ultra-accelerated particles are then whipped around by the nebula's remaining magnetic fields, they radiate the very gamma-ray flares we detect, photons with energies that defy conventional explanation. This process solves part of the puzzle, explaining how the energy is released so quickly and violently. Yet the exact trigger for the reconnection event remains one of the nebula's most guarded secrets. What is the final straw that causes these magnetic fields, holding their tension for so long, to suddenly and catastrophically snap? The answer lies hidden within the turbulent chaos just outside the pulsar, a place where physics is pushed to its absolute limit. This violent nebula even creates solid matter from its own chaos. We know that supernova are the universe's primary factories for cosmic dust, forging the microscopic grains that will one day form new planets and even life itself. The Crab Nebula, as the remnant of such an explosion, should be no exception, yet its environment presents a brutal paradox. The space here is flooded with the pulsar's intense radiation and battered by a relentless storm of high-energy particles, conditions that should shred and vaporize any dust grains almost instantly. The very forces that give the nebula its beautiful glow are the same forces that should make it a dust-free zone. And yet, clear observations, particularly from infrared telescopes, have confirmed that dust is indeed present. This detection creates a profound enigma. How can something so delicate persist in a place so violently hostile? One possibility is that the dust is forming in sheltered pockets, within the densest and coolest parts of the expanding filaments. Here, the gas might be thick enough to act as a temporary shield, allowing atoms to clump together into solid particles far from the pulsar's direct glare. But survival is only half the mystery. The other, more radical idea is that the dust is not merely surviving, but is being continuously replenished. The pulsar's own wind, as it slams into the nebula, could be creating regions of such extreme pressure and density that new dust grains are constantly condensing into existence. A perpetual cycle of creation and destruction happening right before our eyes. This would mean the Crab Nebula is not just a relic of past dust production, but an active, ongoing forge, fighting against its own destructive heart to seed the cosmos with the raw materials for future worlds. Even the outermost edges of this cosmic cloud are not still. Deep within wide-field optical images, far beyond the brilliant filaments, astronomers have detected vast, faint ripples. They curve through the nebula's distant halo like gentle waves on a cosmic shore, almost too subtle to see against the darkness of space. These are not the turbulent structures driven by the modern pulsar, but something far more ancient. They are likely a fossilized echo of the very first moments of the explosion, the primordial shock wave from the supernova as it continues its journey outward. But this shock is not expanding into a perfect vacuum. It is plowing into the ghost of the star's own past. In the millennia before its death, the massive progenitor star did not die quietly. It was a bloated, unstable giant, shedding its outer layers in a powerful stellar wind, much like a tree steadily losing its leaves in an autumn gale. This wind carved out a cavity in the surrounding interstellar medium, a bubble of tenuous gas that remained long after the star itself was gone. When the supernova finally erupted, its blast wave raced through this pre-carved space. Now, 1,000 years later, that initial shock front is finally catching up to the slower, denser shell of that ancient stellar wind. The ripples we see are the visible evidence of this collision, the interaction between the death scream of the star and the final breaths it took while it was still alive. This delicate structure is more than just a pretty pattern. It is a cosmic fossil. By studying the spacing and shape of these ripples, scientists can read the history of the star's final chapter. They can estimate the strength of its stellar wind and understand the conditions in its immediate environment just before the cataclysm. It is a tangible record of the star's life, etched into the nebula's outermost reaches, a silent testimony to the long, slow decay that preceded its sudden, brilliant end. This frantic spinning is not free. The Crab pulsar pays for its incredible activity with its own rotational energy, and the price is astronomical. Every single second, as it spins 30 times, it loses a staggering amount of power. The rate of this energy loss is almost beyond comprehension, equivalent to the total energy output of 100,000 stars like our Sun, all vanishing in the blink of a cosmic eye. Where does all that power go? It does not simply disappear. This colossal drain is the very fuel that ignites the entire nebula. The pulsar's slowdown is the ultimate power source, the cosmic battery that illuminates everything we see. That energy is transferred directly into the pulsar's relentless magnetic wind and the intense radiation that floods the surrounding cloud. From the brilliant X-ray ring shimmering at its heart to the faint, steady radio glow of its outermost filaments, every bit of light, every surge of power, is a direct withdrawal from the pulsar's own spin. Think of it as a cosmic flywheel, a gigantic spinning top that is gradually winding down. As it slows, its stored rotational energy is converted with breathtaking efficiency into the magnetic storms and particle hurricanes that animate the nebula. This makes the Crab one of the most efficient engines we have ever observed in the universe. There is no waste, no lost power. The slow, inevitable death of a spin directly translates into the vibrant, violent life of a nebula. How long can this continue? The pulsar will keep spinning down, and one day, in the distant future, its rotations will become too slow, its energy output too feeble to power the brilliant cloud. The very force that gives the Crab its life is also counting down to its final dimming. This spinning heart of the Crab might be wringing the very fabric of space-time. Beyond the intense light and radiation, the Crab pulsar is a prime candidate for producing one of the universe's most elusive signals: continuous gravitational waves. These are not the violent ripples from colliding black holes that LIGO has already detected, but a faint, perpetual hum, a single, unwavering note sung by the pulsar's rapid rotation and its imperfect shape. For this to happen, the pulsar cannot be a perfect sphere. Even a minuscule deformity on its surface, a mountain no taller than a few centimeters, would be enough. Given the pulsar's incredible density, that tiny bump would have the mass of a large asteroid, and as it spins 30 times every second, it would whip through space, rhythmically distorting the space around it. This creates a constant, faint tremor in spacetime itself, a signal that observatories like LIGO are desperately trying to hear. Detecting this hum would be a monumental breakthrough, far more than just checking another phenomenon off a list. It would open a completely new window into the pulsar's secret interior. The strength and frequency of these gravitational waves would tell us directly about the star's internal composition, probing regions that light and other radiation can never reach. Is the core a bizarre soup of free quarks? Is it a solid, crystalline mass of neutrons? Or does it contain a superfluid so perfect it defies our understanding? Each of these possibilities would affect how the star responds to its own immense gravity and rotation, changing the precise nature of its gravitational hum. Finding this signal would be like a doctor using a stethoscope for the very first time, allowing us to listen to the heartbeat of a neutron star and finally diagnose what lies beneath its impenetrable surface. The Crab Nebula's story does not end at its visible edge. For now, its expansion is largely a journey through near emptiness, but this will not always be the case. It is racing toward a fateful encounter with the thin, scattered gas that fills the space between the stars, the interstellar medium. This interaction is currently faint, a whisper against the nebula's brilliant roar, yet it marks the beginning of a transformation that will unfold over many thousands of years. The outermost filaments, still moving at tremendous speed, are starting to plow into this diffuse material. Imagine a ship sailing on a calm sea suddenly entering waters choked with floating seaweed. At first, the effect is minimal, but over a vast distance, the constant, gentle drag begins to slow the vessel. This is the future of the crab. As the decades turn to millennia, this friction will gradually sap the nebula's outward momentum. The expansion that began with a cataclysmic blast will slow to a crawl. The shock wave that currently carves its way through a near vacuum will instead begin to pile up the interstellar gas in front of it, compressing and heating it until it too begins to glow. The nebula's beautiful, sharp filaments will blur and soften, their distinct shapes merging into a broader, more diffuse shell. This slow-motion metamorphosis is not unique to the crab. It is the inevitable life cycle of every supernova remnant. By creating computer models of this process, astronomers can peer into the nebula's distant future. They can simulate how its luminosity will change, how its structure will evolve, and how it will ultimately recycle its enriched material back into the galaxy. This faint, current interaction is a preview, a single frame in a cosmic film that shows how the violent death of one star slowly, patiently, sows the seeds for the birth of future stars and planets. This celestial maelstrom of unpredictable flares and shifting light has an unexpected day job. For all its violent outbursts, the Crab Nebula serves as one of the most crucial calibration tools in modern astronomy. Across much of the electromagnetic spectrum, its output is remarkably steady, a predictable beacon in the high-energy sky. This reliability has earned it the role of a cosmic standard candle, a fundamental reference point against which all other sources of X-rays and gamma rays are measured. When a new space telescope is launched or an existing instrument needs its vision checked, scientists often point it toward the crab. They already know, with great precision, how bright the nebula should appear in these specific wavelengths. Any deviation in their instrument's reading reveals its unique quirks and sensitivities, allowing astronomers to fine-tune their hardware and software for absolute accuracy. It is the universe's own certified light bulb, a consistent source against which the dimmest flickers and the brightest novas can be reliably quantified. This creates a beautiful paradox. The very same object that produces inexplicable gamma-ray flares, sudden bursts of chaos that defy our models, is also the bedrock of stability for an entire field of science. Its wild heart and its steady hand exist in a delicate balance, one allowing us to explore the frontiers of the unknown while the other provides the trusted map we need to navigate. How many other cosmic wonders hold such contradictory roles, acting as both the rule and the exception in our quest to understand the universe? Our most beautiful simulations of this cosmic engine fall short of its chaotic reality. We can create stunning digital models of pulsar wind nebulae, depicting them as elegant, symmetrical bubbles inflated by a steady wind from a perfectly centered star. These simulations are masterpieces of theoretical physics, but the Crab Nebula stubbornly refuses to follow their graceful scripts. Its glaring asymmetries, its unpredictable knots, and its violent gamma-ray flares are constant reminders that nature prefers complexity over our clean, mathematical ideals. This is not a failure of our science, but a challenge that pushes it forward. The messy truth of the crab forces physicists to move beyond simplified assumptions and incorporate the raw, untamed physics of real cosmic environments. The key ingredients our models are now struggling to include are plasma instabilities and turbulence. Think of plasma as a fourth state of matter, a superheated gas so energetic that electrons are torn from their atoms, creating a seething soup of charged particles. This plasma is not calm, it is inherently unstable, prone to forming whirlpools and eddies that break apart orderly flows. Within the crab, this translates to the sudden formation of bright knots in the jet and the rippling, wave-like structures in its inner ring. Turbulence takes this chaos to a cosmic scale. It is the same phenomenon that creates unpredictable whirlpools in a fast-moving river, but here it operates within a magnetic storm of relativistic particles. This turbulence shreds smooth shock fronts into tangled filaments, and drives the magnetic reconnection events that trigger those impossible flares. Our most advanced models are now being fed this richer diet of physics, but the Crab Nebula remains the ultimate benchmark. A simulation is only considered successful when it can not only reproduce the nebula's beautiful shape, but also its wild and unpredictable heart, a testament to a universe that is always more inventive than our imagination. The final chapter of this cosmic marvel is already being written across a timeline that dwarfs human history. Over the next 10,000 years, the vibrant engine at the heart of the Crab will slowly run out of fuel. The Pulsar's frantic spin, already slowing from its incredible birth rate, will continue its gradual decline. As its rotations grow more lethargic, the energy it can inject into the surrounding nebula will steadily diminish. The brilliant synchrotron glow that defines the Crab today will begin to fade, like a magnificent firework dissolving into embers. The fierce blue-white light will soften, and the intricate filamentary structure will grow dimmer and more diffuse. The nebula itself will continue its outward journey, but it will no longer be a pulsar wind nebula. It will transform into a more typical supernova remnant, a shell of gas expanding into space, its luminosity sustained only by the fading heat of the ancient explosion and the shock of its expansion. Meanwhile, the pulsar's own dramatic escape will reach its conclusion. Racing across space at hundreds of thousands of miles per hour, it will finally break free from the expanding cloud of its own creation. It will leave the beautiful, fading nebula behind, a ghost ship sailing away from the port it once illuminated. The pulsar will journey on alone through the galactic void, a dark, cooling cinder of ultra-dense matter. Its lighthouse beams will have long since flickered out, its magnetic dynamo grown quiet. It will become a silent wanderer, a fossil from a cataclysm witnessed 1,000 years ago, carrying the memory of its brilliant but temporary partnership into the endless dark. The Crab Nebula, as a singular, active entity, will cease to exist, its matter slowly dispersing to eventually mingle with the raw material for future stars and planets, completing the great cosmic cycle of death and rebirth. From its runaway pulsar to its phantom wisps and violent gamma-ray heart, this journey through 30 cosmic riddles reveals a celestial object in constant, turbulent motion. The Crab Nebula is far more than a beautiful fossil. It is a dynamic laboratory where the most extreme physics in the universe is on brilliant, chaotic display. It demonstrates the universe's dual nature with breathtaking clarity, a place where a single act of stellar destruction forged an engine of persistent creation. This cloud of debris is actively reshaping its own environment, forging new matter, and accelerating particles to energies we cannot hope to replicate. Its story is a testament to the endless cycle of death and rebirth that governs the cosmos, where the end of one star provides the very ingredients and energy for the next generation. So the next time you look up at the night sky, find the constellation Taurus and know that within it glows this faint, enduring testament to cosmic violence and beauty. Which of its many phenomena left you in the greatest awe? Share your thoughts and consider seeking out this celestial wonder for yourself, a direct glimpse into the heart of a star that died 1,000 years ago, yet whose light and lessons are more alive than ever.